Alrighty, folks, welcome back, and this will be our last lesson on model building, and then we're going to go into the lesson number 5, and we're going to be talking about um, oh geez, brain fog for a second here. The assumptions that we need to make when or the assumptions that have to hold true when we're actually creating these models. So right now, what we are doing is we're not assessing any of the assumptions that need to be met. We're simply just let's build the model, and once we figure out what model we are actually going to deal with, then let's go through and let's assess, making sure that those assumptions of, say, linearity, the normal distribution in terms of the response variable, all of that stuff is taken into consideration. We'll look at the different tests for being able to do that. A lot of it's going to be visual, but we'll get to that in lesson number 5. So let's finish up the model building now. All right, so what have we done up to this point in time? Well, in terms of model building, we looked at very first multicollinearity. So again, talking about when predictor variables are highly linked to one another. So basically giving the exact same information. When we can remove them and should remove them or should not remove them. We've talked briefly about that. There's no hard, fast rule on that one. But we looked at the variance inflation factor as a tool for being able to help determine whether or not something is creating multicollinearity inside of our model. And then we looked at different metrics of being able to assess a model. That was in the last lesson. So right now we are looking at being able to automate some of these things. So we're going to look at in this lesson 3 iterative methods that will be used not independently, kind of in conjunction with what we've been doing up to this point in time. So the 3 models are forward selection, backwards elimination, and a combination of the 2, which is going to be a stepwise selection. Now, these are iterative methods, so that means that they go through step by step by step by step of constantly trying to either add things to the model, remove things from the model, or actually doing both, which we'll see in the stepwise selection. And then at the end of it, there's going to be some stop criteria. Once we hit that criteria, then what we end up with is the predictors that we are going to have inside of our model. Now, there's a number of different ways in which we can have these sort of stop criteria and what we should add and what we should not add. We are going to be doing this based upon the p-values. So when we create our model and we ask for the summary table, that summary table gives us the p-values. So if we were to do a hypothesis test for each one of the predictors that we would have in there, that p-value helps us being able to either accept or reject, or sorry, not accept, reject the null hypothesis or fail to reject the null hypothesis. I shouldn't say accept because we don't accept it, we just fail to reject it. But that's going to be the criteria that we are going to be looking at here. As I said, there's other ones, but for now, we're just going to be dealing with the p-value for this. All right. So in terms of the slides here, so at each iteration, a single independent variable is added or removed from the regression model. I should say, or both, if we are dealing with option 3 of the stepwise selection, and the resulting model is evaluated. So we did talk about this beforehand. Or this might have been a question on something. When we are looking at the model in itself and when we can take things away and when we can add things in, all of this we are doing one predictor at a time, and then we're reevaluating the model. So as we saw in one of the examples, that when we took one of the predictor variables out, what happened? This calculated the different p-values for all the remaining predictor variables inside of there. So it's not like we can simultaneously remove multiple, it's just one independently at a time, then the new model's reassessed. Both methods are generally acceptable ways to obtain a model, but they do not always result in the same final model. So basically what I'm talking about here when I say both methods, I'm talking about the forward selection and backwards elimination. The stepwise selection is a combination of those two. But really that's it. So they are acceptable ways of being able to obtain a model, but it doesn't guarantee that we are going to get exactly the same model in the end. And when we go through the different steps of this, we'll see exactly why that is. So let's jump into the remaining, or the steps involved in this. So we'll start with forward selection. All right, so to perform forward selection, we select a significance level. So we're going to pick some alpha, and we're going to call this alpha sub enter. So the general idea is we start off with a model with no predictor variables in there. So we need to be able to put a predictor variable inside of there. And this is where those p-values are going to come into play. And this is going to be where that alpha enter is going to come into play. There's going to be some threshold. So these things have to be significant enough to be able to enter our model. So this gets us into step one. So step one is we fit a regression model with no independent variables whatsoever. So we basically have the model and we have the intercept. We have the mean of this. Step two, now we want to add in a predictor variable. So what do? So the independent variable with the lowest p-value, less than alpha enter, will be added to the model. So we basically consider all possible models with just a single predictor variable, and whatever model gives us the lowest p-value in regards to that predictor variable, that is going to be the one that enters into the new model, or the model that we are in fact building. Now, when I say it's going to be the one that enters in, it has to have the criteria that whatever that p-value is has to be less than our alpha enter. So if we set our alpha enter to be 5%, so 0.05, all of our p-values would have to be less than that. So they would have to be, that's that level of statistical significance we are in fact looking for. All right, so that's step two. Now step three, if every independent variable with a p-value less than alpha has been added to the model, we've arrived at the final model. So basically we repeat this step over and over and over again. So again, first step, we build the empty model. There's no predictor variables inside there. We are just looking at the average of the response. We add a single predictor variable, but we look at all models with a single predictor variable, pick the one with the lowest p-value. So now we have one predictor variable inside of there. Now we want to put a second. So we look at all models with two predictor variables and that original one still in there. So with that new predictor variable we're adding, we are looking at adding the one with the lowest p-value. Again, it has to be less than alpha enter. And then we just keep repeating this process over and over and over. So think of it as soon as we add something in there, it's stuck in there. We're not removing it whatsoever. We are now just assessing when we add a new value in there, a new predictor variable, what is its p-value in relation to alpha enter. Now do keep in mind, this is kind of where the idea for the third iterative method comes into play. Once we add a predictor variable, all the p-values change. Now it is possible that a predictor variable we entered previously now has a p-value that is larger than alpha enter. But because of this method, we don't even consider that. We will consider that in the stepwise, but we don't even consider that it's changed here. We are only looking at the p-values of the new predictor variable that we are in fact entering here. And once we've repeated this process, so we iterated over this enough times that we no longer have a predictor variable that we can put in there because all the p-values are, say, greater than what alpha enter is, then we stop. That is our stop criteria. We hit there. This is our model. Okay, so let's look at option two. This is the second iterative method. This is backwards elimination. So forward selection, what we started with was the empty model. Here what we're doing is we are starting with a full model. We still have that alpha, but it's not alpha enter anymore, it's alpha sub stay. And we predefine these in advance. This could also be the 0.05 or the 5%. 3 steps as well. So the first step is we build a model with all the variables inside of there. We don't care multicollinearity, anything else along those lines. Everything is just inside of there. Now we want to remove predictor variables. So what do? I run that summary table. I don't actually do this because this would all be done for us. We think of it as we run the summary table. We look at, okay, what are the highest p-values? What are the p-values that are greater than alpha stay? So if alpha stay, again, is that 5% or 0.05, we look at all the p-values that are above that, are larger than that, and we grab the largest one and say, out you go. So as soon as we kick that one out, again, all of the remaining variables in our model, all of those p-values will change. And then again, we repeat the process. So second iteration of this now, I'm one less predictor variable inside of there. I look at the new summary table, the new p-values, and I say, okay, what are all the p-values that are greater than alpha stay? Then I grab the largest and I kick that one out. Again, repeat the process. As soon as that one's kicked out, I run a new summary table, new p-values. We keep going and going and going until I have nothing left to kick out. Okay. This is why we potentially don't end up with exactly the same model, whether or not we're following the forward selection or backwards elimination. Because the process of this is, again, we're adding things to it, and this one we are removing things from it. And depending on which one we remove, it's going to adjust all those p-values. And depending on which one we add, it's going to adjust all of those p-values. And here's the thing, again, as we saw beforehand, if I remove something, I'm going to adjust all of those p-values. So what happens if I pick the largest one and I kick that one out because that's what the algorithm tells me to do? Well, what happens if instead I kicked out the second smallest one? And I kicked out the second largest p-value. And if I kick that one out, then the one that was the largest now drops into the alpha stay criteria, and I actually don't end up removing that one. It's a possibility. But again, it doesn't. That's not how the model is kind of defined. So this is kind of where we will end up with potentially two completely different models. Sometimes we'll end up with the same one. Sometimes we'll end up with two completely different ones. And again, this doesn't take multicollinearity or any of the model assumptions into consideration. This is just simply looking at the p-value. So think of it as it's always constantly running that hypothesis test. Okay, let's look at the last one now. So a combination of the two. So to perform a stepwise regression, we select two significant levels this time. So we have two alphas. We have an alpha stay and we have an alpha enter. Step one of this, we consider all possible models containing one independent variable. So again, think of it as we're starting in exactly the same way we did with forward selection. We have the empty model, or not empty model, but we have the model with no predictor variables. Now I want to add a single predictor variable. So I'm going to pick the one that has the lowest p-value based upon alpha enter. Then I'm going to put that variable inside, and we're going to call that x sub 1. Okay, so that's step one done. Step two, I want to add a second predictor variable. Okay, so we might think now, this seems a lot like the forward selection. Okay, but here's where the twist comes into play. So we do the same thing. We look at all models with two predictor variables, with that first predictor variable still in there. And again, we're looking at those p-values. And I want the p-value with the smallest p-value that's within that alpha stay, or sorry, that alpha enter criteria. So we put that, whatever one it is, we put that in there, and we'll call that x sub 2. Here's where the change happens. Now with that new model, with two predictor variables inside of there, we reassess the model as a whole. So we are going to run, say, a new summary table. We have all of those new p-values. Now I go ahead and I look. I don't need to look at the p-value that I just added in because I just added that one in. It adjusted for all the others inside of there. So I know nothing in that one is going to change. It's going to stay. But as I said, all the others have been adjusted. Well, just the first one has been adjusted. So that x sub 1. So I look at that x sub 1. I'm like, okay, because I added x sub 2, is x sub 1, is the p-value for that still statistically significant based upon our alpha enter? So we have an alpha stay, sorry, I said that wrong. Alpha stay, we have an alpha enter, which is to enter the model. We have an alpha stay, which means after we've reassessed the model, is it still viable to stay in here? And let me emphasize this part, alpha stay and alpha enter do not have to be the same. So we could potentially have an easier requirement to get inside of the model, and then once we're inside of the model to stay, we might have a harder criteria, or vice versa, perfectly fine. But this is where those two competing factors kind of come into play. So the addition and possible subtraction of things once we reassess the model. So the x sub 1 was in there the first time around, the x sub 1 and x sub 2 was in there the second time around, but at the end of that second time around, it is possible that x sub 1 has to go away because it just doesn't meet that criteria. So that would have been step 3 that I kind of just highlighted over there. So a couple of things here to note. So if x sub 1 is no longer significant, remove it from the model and repeat step 2. So only x sub 2 would still be in there. Then we look to add in a new predictor variable, so on and so forth. So we repeat that process. And every time we add a new predictor variable, again, all of the p-values update. So what we need to do is we need to reassess all of those p-values And do they all meet the criteria for alpha stay? So are all the p-values less than alpha stay? If so, awesome. If any of them have changed and become larger, then out you go. That's it, that's all. So if x sub 1 is still significant, then consider all models containing 3 independent variables and so on and so forth. As I say, we just keep repeating through this process. Add something in, reassess the model, kick something out if need be, and then again, keep reassessing and going and going and going from there. Now, if there's multiple things that have changed, again, we're not simultaneously kicking out multiple things. It's only one thing at a time. So to kick something out, if there's a couple of variables that no longer meet that threshold, it's going to find the one with the largest p-value, and then out it goes. And then again, the stop criteria is once we cannot add and we cannot remove anything from there. That's it. That's all. And the stop criteria is going to be based upon the alpha stay, alpha enter, which again, do not have to be the same. All right. So for exercise 5, let's run through this. So what we want to do is, again, still dealing with the same data set that we have before. We want to build a model using the backwards elimination. We want to build a model using the forward selection, and we want to build a model using the stepwise regression. So let's jump over to R. Ooh, exciting thing. So the Amazon Prime Day was coming up here, and there's a cool little device that kind of works for capturing audio and capturing video. So got a new camera, got this new device, new microphone, and it's also going to allow me to switch in between my screens without having to try and find my mouse every single time. So really excited about this. I'm not sure I'm going to be able to use it for this term. So you're still probably going to have to listen to me go, where's my mouse? But moving forward, might actually have to create some better content for this sort of thing. Yay. Which all of this is posted on my YouTube channel, so I'm going to start creating some other stuff up there too. So if you're interested in any of this stuff, going to be focusing more on the data science side of things. So if you're interested in that, stay tuned. More to come. Yay. But back to the material. Where's my mouse now? And there we go. Switched up. So I haven't erased everything. It's still all here from our last lesson inside of R. So let's just play around with this now. So again, we want to do a backwards elimination. We want to do a forward selection. So I'm just doing this in order of the slides, which you can see up top here. So A is backwards elimination, B is forward selection, and then the stepwise is part C of this. All right, so let's start with the backwards elimination. So again, this is all using that OLSRR library that we downloaded and installed last time around. So the first thing that we want to start with, regardless of which model or which operation or iterative method we are dealing with, we want to build the full model. So this is happening in line 95. I'm going to call this fit all. So we're using that LM function, that linear model function. We're saying sales, that's our response, is explained by, that is our tilde, and then we have the period, which means I want all of the predictor variables. So it's the full model in there. This is all coming from the data, which is the sales pref data frame. Okay, so I've built the full model now. Let's just, down in the console here, because I want to show some of these. Some of these have changed over the period of time. Let's just call up the help function. So I'm going to do help OLS underscore step underscore backward. Now notice the autofill here is all of the different functions that start with the OLS underscore step underscore back. Backward is obviously the pre-filled in here. But do notice that there is other criteria in here. We could do this all about the adjusted R squared. We could do the AIC, which we haven't talked about, just another metric for being able to assess the model. But we are sticking with the p-values on this one. So I'm going to do the OLS backward underscore p. Okay, so let's just run this one here. And the help file shows up in our bottom right. So how do we use the function? We just include the model. So there is some defaults in here. Let's see. So the p-value, this is going to be our p So we're doing the backwards elimination. So this is the p stay, or sorry, the alpha sub stay. So I'm just defining what this is going to be. So it's not calling it alpha, it's just p underscore value. We can set it to whatever it wants to be. We can see by default here it's set to 0.3. We don't need it set to 0.3. We can change whatever it wants, but again, by default it is set to that. There's a smattering of other things that we can do. So there is an include, which is a character or numerical variable or vector, sorry. So we can make sure that specific predictors are in fact included, or specific ones are in fact excluded from the model. Couple of other things. You can go through all of this yourself. The big one for us is just setting that p-value. And notice that the model, an object of class LM, the model should include all candidate predictor variables. So again, that is the full model, which we've already created and called fit all. So what I'm going to do is I'm going to run the OLS underscore step underscore backwards underscore P fit all. That's our model. So that is our first parameter that is going in here. The second one, P underscore val for the P value. We'll set that at 0.05. So again, we're doing that backwards. So it's starting with the full model and we are kicking things out. We're kicking out everything that doesn't meet that criteria. Okay, so if I run this one here, down in the console, we'll see. Let's make this a little bit bigger for us. So just working our way up to the top, it gives us a lot of output here. We don't necessarily need it all, but now it's kind of just telling us again, going through the different steps, what our model is and what it's doing to kick things out. And again, this is all based upon the p-value. So at step 0, we have the full model. Nothing's been kicked out at this point in time. So now it looks at that summary of the full model going, okay, what is the one with that largest p-value? And we, again, if we remember from this beforehand, ratings was the one that had that largest p-value. So that had to go. So now we have 8 predictor variables. We're down to 7 predictor variables. We reinitialize the new model. So the new model is going to have all of these p-values change. And we get on to step 2. So step 2, we look at this reinitialization of our model, look at all the p-values and go, okay, well, which one is greater, or which are the ones that are greater than alpha sub stay, and what's the largest of this? We'll kick that out. That's workloads. So ratings gone, workloads is gone. By the 3rd iteration, we kick out accounts, and last but not least, we kick out change. So those are the 4 things. We're left with a model of size 4. So the model that we had come up with was the first 5 predictor variables based upon none of these sort of techniques, but just again in terms of the multicollinearity and the different metrics that we in fact saw, as well as the cross-validation that we did in the last lesson. So this one's not exactly the same model as the one that we chose from, but again, still meets the criteria of what we want with in terms of being the significance of each one of the predictor variables. So we get the final model output. So we have the R squared, adjusted R squared. So this is 0.96, 0.875 for the adjusted. RMSE, 414, which again doesn't really tell us all that much unless we're looking to compare different things. And a couple of smatterings of other things as well. We have the ANOVA tables and we have the parameter estimates here. So we have what is included into the model. So we have the intercept, we have time, market potential, advertising, and market share. We have their specific estimates, we have their standard error, and so on and so forth. We have the t-values, the p-values, the significance of each one of these. So everything is there for us. So again, we know which ones we kicked out and we know which ones stayed. Now we want to do exactly the same thing, but this time with the forward selection. So this time we are starting, and let's do the help file again. Let's see if anything has changed in this. So go down to the console. Now, one of the cool things about the console is all of the commands that we've done previously are already saved in here, so I can just use the up and down key to get me to the previous one. So if I go up twice, help OLS, so let's back this up a bit, and I don't want backwards, I want forwards. Let's just get rid of some of these. I don't need this. Forward underscore P, that's the one I want. Does anything change here? So again, the p-value by default is set to 0.3. We can adjust that. In terms of the model, again, should include all candidate predictor variables. So as I said, it's always going to include the full model. It builds from there. So we're going to change the p-value to 0.05, fit all as that first parameter that goes inside, which is our full model. If we run this, same idea. Gives us a whole whack of different things here. Let's just bring this screen up. So our model of what's in here now is accounts, advertising, market potential, and market share. Accounts, advertising, market potential. Is that the same thing? Accounts, advertising. Accounts, advertising. Yeah, so it gives us the same model in the end. So this time, what is the process of this? We start off with that base model with nothing inside of there. Then we want to add in that first predictor variable. So that's going to be the accounts. Now remember, accounts, that's the one that had the high multicollinearity with time, with the going through brain fog now. The years of experience or something along those lines. I have to go back and double check these ones. But yeah, it was one of those ones that had the multicollinearity that we removed. Because it had the highest VIF out of everything. But this doesn't take any of that into consideration. So it was the first thing that added in because it had the lowest p-value. Advertising was added in. Market potential and market share was the last two. And of course, we're going to have exactly the same sort of outcomes in terms of the adjusted R-squareds and whatnot. Actually, these are slightly different, I think. I was reading the... see, there we go. This is why I shouldn't be doing these videos in real time. And I should be doing them in front of the class so I have people going, hey, that's a mistake. Yep. So this was our last model. It was time, market potential, advertising, and market shares, not accounts. That's the big difference. So it is a different model that we get in the end. Perfect. That's what I was hoping for. That's what I was thinking. I'm like, I've done this enough times. It shouldn't be the same. Why is it the same this time around? Because I was reading the wrong thing. Crisis averted. We're good. Let's come back to this. So yeah, it is, since it's not the same model, that's why it doesn't have the same adjusted R-squared or any of that fun sort of stuff. So there we go. But again, gives you everything that you need for the parameter estimates of what is kept in or what is included into the model. Okay. Last but not least, that was probably a little too loud, but the excitement was all there for us. So we're going to do the stepwise regression. So this is OLS underscore step underscore both underscore P. So let's look at the help file for this one. So help OLS underscore step underscore both. And I want the p-value approach to this. So here we don't have just p underscore val. We have p underscore enter and p underscore remove. So that is our alpha enter, alpha stay. So by default, enter is 0.1, remove is 0.3. So again, we can keep the defaults in there and see exactly what we get. We'll get completely different models for these sort of things, but this is where that level of significance that we are doing here. So let's go by default. We are keeping exactly the same ones here. Actually, let's change this a bit. So let's go alpha enter. Let's change this to 0.06 and remove 0.55. Actually, let's do alpha enter being 0.1. Let's make it easier to get into the model, but harder to stay into the model. So we'll change this to 0.6. There we go. 0.06, I should say. You can run this as 0.05 and 0.05 as it is in the code originally, or you can change this, or you can play around with this on your own and get completely different outcomes of this. Perfectly acceptable too. All right, so let's run this, see what we get. And of course, I want to move this over. All right, so stepwise, we start off with that base model again. So what's going to be added? Accounts is going to be added, advertising is going to be added, market potential and market share are all added. But notice nothing has in fact been removed. So maybe that 0.06 is a little too high. Let's bring this down to 0.04. 0.04, there we go. So easy to enter, but harder to stay. Do we end up with the same thing? Yeah, we haven't removed anything. Okay, so let's change that or enter criteria. Let's go 0.3, 0.4. I want to see something kicked out of this. Here we go. Here's some changes. Perfect. All right, so the first step is that base model. The first iteration around it counts as added. The second, advertising. Then added market potential, market share, change. Okay. Now, as soon as we've added change, again, everything is reassessed. And what's noticed is change is then removed. Because it was able to be added in because P enter was 0.3. But then when we reassessed whether or not it could stay, P removed was 0.04. So that becomes problematic. If we were to adjust this one, and the same thing happens with time, it was added, then it had to be kicked out. So let's make this a little bit bigger here. Let's move this up to 0.5. We'll do 0.55 actually. There we go. Easy to enter, still harder, but less hard to get removed from here. No, same idea, change in time. Okay, so let's try one more. Let's bring this up to, let's call this 0.1. There we go. Nope, failed again. Okay, so change in time, they're still there. But again, you can play around with this as much as you want, setting that level of significance. I probably wouldn't put these up too high, or at least the P remove. I would probably drop that down depending on, again, that level of significance that we want from there. I'm just trying to build things and keep them inside of here. But again, we can see when things are added, when they're removed. That's the plus and the minus signs of all of this. So the final model that we get is accounts, advertising, market potential, market share. So this is exactly the same as what we got with the forward selection method. So the backwards elimination got us, what did it get us now? Let's scroll up here for a bit. Time, market potential, advertising, market share. I feel this is very, very similar to the model that we had created, except for change, I believe, was the one that we kept in there. But if we were looking at that specific p-value, I think that p-value was like 0.55 or something, or 0.055 or something along those lines. So this is a hard cutoff at this point in time of the p-value of being 0.05. So what we decided to still include there, because it wasn't 100% statistically significant in terms of that specific alpha that we had set, it was very, very close to there. So maybe we did want to add it, maybe we didn't. We decided to keep it in the end because it gave us more a better model overall. And even in terms of, again, the cross-validation, we saw that it was the better model overall. But these are, again, just different techniques for being able to do that. Okay, so those are our iterative methods. I think one last thing that we kind of want to talk about. So with the iterative methods, again, what this does through each iteration, it's either we are going to include something or we are going to remove something, but there is always that update that happens. So when we include something, the model updates. When we remove something, the model updates, because every time we do that, the p-values are going to change. So we need to reassess that. So the question then becomes, is it possible to remove multiple multiple predictor variables at the same time without losing anything in regards to the model? Now, we can't do that with just the p-values. We have to look at something slightly different, and this is what's known as a partial f-test. So let's take a look at that one. So we've already done the f-test to help determine the significance of the model as a whole. The partial f-test is, again, for a partial model. And we'll explain exactly kind of what that, not exactly kind of, we'll explain exactly what that means. I don't know why I threw kind of in there. Working on those things, adding redundant, or not redundant, but words that just don't need to be added into the whole thing. Okay, so partial f-test. In addition to an overall f-test for the model, or an individual t-test for each independent variable, we can perform a partial f-test to assess the significance of a subset of independent variables. So again, if we are looking to include or remove a subset, this is the test that we want to use to be able to do that. So a partial f-test can be useful in several situations, such as when concerning the significance or considering the significance of one, a qualitative variable involving two or more dummy variables. Okay, so we saw when including a dummy variable, and we'll see this again, maybe certain levels individually are not that statistically significant. But if we look at including that dummy variable as a whole, going, is this adding something to the model as a whole? This is where I want to run a partial f-test. So it's either am I going to include all the levels or am I going to not include all of the levels? Higher terms in a polynomial model. So a partial f-test is also good for that. Why is it also good for that? Well, here is the problem. And think for a second where this problem might be coming from. The hint is the beginning of these slides. It didn't freeze. Just trying to give you time to think about this one. The issue is that multicollinearity. If I raise a variable that I have already to a higher power, or I start combining variables together to look for interactions, I am creating this multicollinearity inside of there, which I know is going to inflate my standard error, which is going to decrease my test statistic, which is going to increase my p-value, which is going to interfere with running that hypothesis test for the significance of that variable. So how do we counter that? The partial f-test is going to help us do that. And for 3, a subset of independent variables that are particularly expensive to measure. So sometimes that's going to happen as well. I don't want to try and measure them individually to run these sort of tests. If I could do this as just a one overall, excellent. That's where we want to go with this. All right, so in terms of the model, and we're talking about a subset of variables. So what we're talking about is, think of this as we have a full model and we have a reduced model. So the full model contains the additional variables. The reduced model is inside of the full model. So all of the predictors are still inside of there, except not all of them are going to be inside of there. Just a subset of them are. So let's consider the regression model here as follows. So I have y is equal to a beta naught, a beta 1. Why is my mouse not? Hello, mouse. Are you working? What did I do last time for this? All right, well, I guess I'm not going to be able to draw on this one. I'm not going to go play around in the settings just yet. I think that's where I had to go last time to fix this. Damn you, technology! All right. Okay, so where is my mouse? My mouse is here. And it's not letting me... No, because my mouse, I don't... these are not connected. All right, give me a second here. Let's see what I can do. Because I would like to draw on this. No pen. That's... Did this change? No. Where is my mouse? All displays. I only have 2 displays here. All right, well, I guess that's... Yeah, well, tried. Fix it for the next time. Promise. All right. That was enough of a break. Hopefully that was a quick time for bathroom or coffee or something along those lines. Maybe not enough time, but there we go. All right, so we have the regression models. We have x1 all the way up to, say, xk. But we're going to do a kind of a cut here. We're going to break this up until we'll say x1 all the way up to an xg, and then we're going to have an xg plus 1, which is going to take us all the way up to xk. So at some point in time, we're cutting the model off. So think of this g plus 1 all the way up to k being the additional variables that we want to be able to test for. So suppose we wish to test the significance of k minus g, so k being the total, g being the original ones in there. So this additional k minus g independent variable. So again, that g1 all the way up to gk. We're saying, does it make sense to add these to the model? So the hypothesis test is as follows. We're saying h naught is, so the null hypothesis is the beta g plus 1, so the population parameter for g plus 1 all the way up to the population parameter for k, this is going to be 0. So they are not adding anything to the model. The alternative is at least 1 is. So again, think of this as, again, in terms of the designs of experiments, we don't know which one. We're not asking for that, but at least one of them has to be adding something to the model in itself. And that's it. So HA states that at least one variable is contributing to the model. There's my mouse. Here we go. So we refer to the larger model as the complete model. The reduced model is the one that has the x1 all the way up to xg. So the complete model is the one that also includes the g plus 1 all the way up to k variables inside of there. So to calculate a partial F test, we compare the unexplained variation for the complete model. We'll call that SSE sub c. And the unexplained variation for the reduced model, which is the SSE sub r. So the partial F test is as follows. We look at the SSE for the reduced, subtract it from the SSE from the complete. Now, one thing to note, we would say, well, what happens here if, like, is it ever possible to get something negative? So I'm subtracting two things. So is the SSE for the complete ever going to be larger than the SSE from the reduced? So again, we're adding more variables inside of here. So adding more predictors can never increase the SSE. At worst, the SSE will stay the same if the additional predictors have no effect. But at best, the SSE will decrease because the complete model explains more of the variation in the response. So if it explains more, there's going to be less of this outstanding error. Outstanding sounds like it's a great thing, but we're going to have less of this error that we need to worry about. So this is always going to be at least the same size, if not smaller. So this is always going to be positive on top. The x minus k, we're adding on additional variables, so that's always going to be positive. So we're taking, well, what is the difference between the reduced to complete? So what is... how much is explained more by the complete rather than the reduced? And then we have dividing it by, of course, the degrees of freedom, which is the k minus g. And then we're dividing out by the SSE complete by its degrees of freedom, which is the n minus k plus 1 predictor variables. So that's the total predictor variables, including the k plus 1 is including the intercept. So we define the p-value related to the partial partial F test to be the area under the curve of the F distribution having k minus g and n minus k plus 1 degrees of freedom. And of course, we're looking to the right of this. So we've seen this before in terms of the designs of experiments when we are looking at the F statistic and when we can, in fact, reject the same idea in this regards here. So we can reject H naught in favor of the alternative H sub A at a level of significance of alpha if either of the following conditions are equivalent, or conditions hold, not equivalent. They are both equivalent. But we can look at the partial F test. Is it greater than the critical value? So the critical value is that, where is that cutoff point for that F distribution if the null hypothesis is true based upon the 2 degrees of freedom here. We can also do this using the p-value. So if the p-value is less than or alpha, we reject. There we go. All right, so from exercise 4, we concluded that the best model was the one using only the variables. So this was the one that we had created using, again, the cross-validation as well to determine this, was time, market potential, advertising, market share, and change. So suppose we wish to consider adding squared and interaction terms to our model. Okay, so we're going to include multicollinearity here, which again will inflate the standard error, which will decrease our test statistic, which will increase our p-values. All right, so although we would like to test the significance of the independent variables in the model, extreme multicollinearity exists when using squared and interaction terms. Thus, t-test would not be reliable, so we would like to perform a partial f-test. So this is going to be our last exercise, which is good because this is already at 46 minutes, and that's probably getting long enough. And this is going to take us a little bit of time to go through. So the first thing that we want to do is we want to find a model with the smallest s and compare it to the compare models using the partial f. Is at least one of the additional interaction squared variables actually significant? Okay, so there's 2 things we're doing. We're going to build a model which contains the 5 original predictor variables inside of there. We're going to take those 5 predictor variables, and as you see here, we are going to square. Where is my mouse? I wish I had my pen. Mouse, where are you? Pen. I'm going to try and do this with a trackpad. So I'm going to take my time squared, my market potential squared, advertising squared, market share squared, and change squared. So I'm going to take that data frame and I'm going to take each one of those columns. I'm going to square them and create new columns from there. Then what we're going to do is we are going to look at all possible pairs. So time and market potential, time and advertising, time and market share, time and change. Market potential, advertising, market potential, market share, market potential, change, advertising, market share, advertising, change, market share, change, all of those interactions. So we're going to build columns, and we're just going to take those original columns and multiply them all together. So once we've created this mess of multicollinearity, but all of these new columns, what we're going to do is we're going to build a model, but we're not going to pick a model with everything inside of there. We want to pick a model with the smallest s, and we're going to look at some criteria that's going to do this. Now, one of the things that we want to hold true in this is I want a model with the default 5 variables still left inside of there. These additional variables that we have right over, where is my hands going to? Right there. There we go. Those ones, not all of them need to stay in there, but we want the 5 original. So we want time, market potential, advertising, market share, and change. Those 5 need to stay. Everything else, some things we'll add in there, some things won't. And then once we're done there, then we can run a partial f-test. That we could say, are the addition of those variables, so the squareds and interactions, do they actually add something to the model, or is the original 5 enough? All right, so let's jump back over to R and do this one last time for this lesson at least. So the first thing I'm going to do is I'm going to create vectors. I'm not going to put these into the data frame just yet, but I'm going to create vectors. So I'm going to create all the squared ones. So time squared, market potential squared, advertising squared, market share squared, change squared. Now I'm going to do all of the different interactions. I'm not going to read all of these off because I've already read them off, and that was enough for once. Now I'm going to build a data frame. I'm going to call this int model sale. It's going to take the original first 6 columns of the sales pref data frame. So it's going to include the response, that's the first, and then the next 5 variables. And then it's going to include the smattering of everything else in here. So int model sales is now the master data frame that we are going to be using. Okay, so I need a new package here, and because I installed this at the very beginning using that yellow bar up at the very top, I should just be able to pull this from the library, and perfect, it did. So I'm using LM subsets now. So why am I using this instead of the OLSRR? Well, because that one didn't have the criteria for being able to determine or being able to say, I want these variables to have to be in there. And that's what I want, because again, I want time, market potential, advertising, market share, and change. Those 5 have to be in the model. The other ones, that's a toss-up. All right, so to generate all possible models, but must include our best subset model, I'm going to use int model all. That's where I'm going to store everything to. I'm going to use the lm subset function. So I'm going to say sales is explained by period. So again, I want all of them in there, but I want to include a vector that's just going to contain the names of the ones that I want to make sure that are in there. So that's time, market potential, advertising, market share, change. And again, I'm using all of this coming from the data frame int model sales. So this is going to build all possible models. This might take a little bit of time. We'll see. Never mind, it's already done. Perfect. Not even a break time needed in there. Now I'm running the summary of this. There we go. All right, so what this does, the first column here, size. So this gives us the number of variables that we have inside of here. I believe there's 21 variables, so that would include, so this would be k plus 1. So this also includes the intercept. Right, so if we include the intercept, the 5 predictors, that gives us 6. The smallest model we could have is just including one of those predictor variables or those new additional variables inside of there. So we have a model of 7. So again, it contains the intercept, it contains the original 5 plus now 1. This contains 2, 3, so on and so forth. So here is the how many models are best. So it's the best model overall. We have our S value for these ones. We have our R squared, adjusted R squared. So what gives us our best S value here? Standard error 174 looks like it's the best, so it could be the 18. So this should also give us the best adjusted R squared, or the highest adjusted R squared, 0.82, 3. Yeah, that looks like it's the best one overall, so okay. All right, so what we're going to do now is we are going to pick. Now, it doesn't tell us, this output here does not tell us what model that is. It tells us the number of predictors inside of there, but not what model it is. So I'm going to use the lm select function. It's going to be used on the int model all, which again is the lm subset function. So it's going to go in there. It's going to pick the best model. So this is going to be the best full. Best full is going to be the 1. Yeah, this is going to be the one of size 18. So I'm going to include, again, the intercept, the ones that we forced in there, so time, market potential, advertising, market share, change. And then what are we not including? We are not going to include QSA. What is QSA for? Oh, Q squared, yeah, the squared of the advertising. Time and change, market potential, and advertising. So those interactions we are not including in here. But everything else we are including in here. So notice this isn't an actual model in itself. This is just giving us the criteria that pick the best one overall and telling us which variables are going to include it in there. So what I can use now is I can use the refit function taken in this lm select function, and it's going to build the full model for me. Now I could do this manually. I can do the lm is the LM function, I'm going to say sales is explained by, and then I can include everything except the three that I wanted to kick out, but this is just an easier way of doing it. So I'm going to use the refit to create this new model. I'm going to call this model full and summary of the full. There we go. So this is going to be our full model. Now, one of the things to notice, this is going to have a high VIF. So let's run the VIF of the full. And notice, again, multicollinearity, it becomes an issue when it's above a 10. And all of these, except for a small handful, are above 10, significantly above 10, which makes sense based upon the fact that, again, we're dealing with squared terms, interaction terms, so we know that this is going to have high levels of multicollinearity inside of there by default, which is why we're not running the t-test. So even if I were to look here in my console, and I wanted to say, well, some of these are significant, some of them are not, and based upon this, I should kick some things out. Well, wait a second. I can't trust these because the standard error is inflated. Test statistics, so those t-values, are all going to be smaller than what they should be. And the p-values are going to be larger than what they should be. So if I were to run this hypothesis test, I can't trust the outcome of this. So what do? Let's run the partial p-test. All right, I'm going to say the reduced model is the sales as explained by time, market potential, advertising, market share, change. So it's going to be that model with 5 variables that we came up with. Now, again, those are the 5 that had to be in the full model. So the reduced model sits inside the full model. The full model just has more variables inside of there. So to run the partial f-test, it's just the ANOVA function. And I put the 2 models inside of there, so reduced and full. All right, so degrees of freedom for the first one is 19. Degrees of freedom for the second is 7. The difference in degrees of freedom we have is 12. Sum of squares difference is going to be 3,303,502 with an F value now. Again, based upon the degrees of freedom, we have an F value of 9.037 or 07. Okay, well, if I knew what that critical value was, I could say whether or not this is statistically significant or not, or is it within the rejection region. There we go. Speaking is not my strong point, but that's because we're almost at an hour here. Again, imagine, these used to be 3 hours long. That would have been really, really long. Not just for you, but for me as well. P-value. Okay, so our p-value for this F statistic is 0.003698. Okay, so if our hypothesis test here, and I would write it, but I can't because I don't have my pen working, but here it is. Our null hypothesis is the additional variables. So I'm not talking about the time, market potential, advertising, market share, change. I'm talking about the other smattering. So all the squared, all the interactions that we've kept, the 3 that we've removed, so be it. But those additional ones that we've added in there, do they add something to the, or sorry, I should say the null hypothesis is they're not adding anything to the model. So the true population parameter, the betas for each one of those are in fact 0. The alternative is at least one of them is not 0. So at least one of them is adding something to the model. So if our alpha is 0.05, and again, by default, unless we state otherwise, it's always going to be 0.05. Here our p-value is 0.003. That is less than a 0.05. So if alpha, or if the p-value is less than alpha, we reject the null hypothesis and accept the alternative, saying that at least one of these squared or interaction terms is adding something to the model. Now, we're not saying that each one is. We don't know that. But the inclusion of all of them does, in fact, help the model statistically significant enough that we want to be able to include them. Okay. So that's our partial f-test. If we wanted to look at that critical value, so again, this is assuming the null hypothesis is true. Assuming the null hypothesis is true, that none of these are adding anything to our model, where should we see the f values that come from this? So again, I want that lower tail to be false because I want the extreme right. I want an alpha to be 0.05, and our degrees of freedom are 7 and 19. So this is going to give me, and I'm using the QF function, this is going to give me a critical value of 2.543534. So that means, again, if the null hypothesis was true, and we ran this experiment over and over and over and over again, that last 5% should see an F value of 2.543534 or greater. Again, that's that remaining 5%. Everything before that we should see 95% of the time. But that extreme 5% of the cases, it's going to be that value or larger. So clearly, an F value of 9.0307 is larger than that, so it's in the rejection region. It's to the right of the critical value, so we reject, again, that null hypothesis and accept the alternative. Okay. So that's it. That's all for today. Thank you for sticking around as always. In the next lesson and the last lesson here, we're going to be talking about those assumptions that we need to make, as well as outliers. And what do we do with outliers? Do we just simply get rid of them? When can we get rid of them? And we'll run through a couple of examples of that as well. But that's it. That's all for today. We'll see you soon. Midterms coming up. If you have any questions, feel free to reach out. Otherwise, we'll see you later. And I've lost my mouse. There you are. Stop recording.